Our first speaker is Vivien Londe, who will talk about towards local testability for quantum coding.
Thank you. Thank you for giving me the opportunity to talk here. So I'm going to talk about quantum locally testable codes. And this is joint work with Anthony Leverrier and Gilles Zémor. Let me minimize this. Okay. So this talk is about quantum codes, and I will start with the controversial sentence that classical LDPC codes are well understood, in the sense that if you pick a random matrix, a parity check matrix at random, it gives you a linear number of logical bits and a linear minimum distance, and you can decode such a code efficiently with a belief propagation algorithm. And what I mean with classical LDPC codes are well understood is, and what I really want to do is to contrast this with quantum LDPC codes, which are way less understood. And first, let me define quantum LDPC codes. So they are defined by constraints that are local, which makes them LDPC. And just like classical LDPC codes, if a state satisfies all such local constraints, then it belongs to the code space, and this is what defines the code. So when I'm saying that they are poorly understood, what I mean is that the best scaling for the number of logical qubits and for the minimum distance is not known for quantum LDPC codes, and it's not always clear how to efficiently decode them. And what I would like to investigate in this talk is what property of a quantum code makes decoding easy. So the first guess for a good decoder for quantum LDPC codes is to use the same decoder as for classical codes, namely belief propagation. But this doesn't work because quantum codes have lots of small cycles. It comes from the fact that they are LDPC. And another approach is to use local decoders, and this works much better for some codes, notably for hyperbolic 4D codes, and also for quantum expander codes. And what's interesting here is that in the case of quantum expander codes, for instance, what makes the decoder, the local decoder called the small set flip work, is that such codes satisfy they have good soundness. They satisfy the following inequality, that the syndrome of an error is at least, well, it is proportional to the size of the error itself. So quantum expander codes satisfy this property, but only for errors that are small enough. And this is sufficient to show that the small set flip decoder works for such codes. And in the case of hyperbolic codes, the fact that local decoder works also comes from inequalities that are very similar to soundness inequalities, namely isoperimetric inequalities satisfied for low weight errors. So having this inequality is not sufficient to say that a code is locally testable when it holds only for small enough errors. It has to hold for any error of any size. And if we had such codes, then there would be some nice implications. And in the case of classical codes, their existence led to some very nice results in complexity theory. So let me now talk more specifically about quantum locally testable codes. The connection with complexity theory is not as clear as in the classical case, but there are some hints that some links with Hamiltonian complexity. And also it has some links, as I was saying before, with good decoders and among others with single shot decoding. So to define formally what a quantum locally testable code is, I first need to have a notion of distance to code and weight of the syndrome. So let me first formalize the notion of distance to code. It's possible to define states that are a distance at most t from the code space, and by taking a weighted sum of states that are a distance at most t but not at most t minus 1, you get the distance operator. And this gives the formal definition of a quantum locally testable code when the Hamiltonian operator associated with this code is greater than this distance operator renormalized. And finding such quantum codes is hard. There are only two non-constructions. The first one was by Matthew Hastings in 2017, and the second one is in this work, and it gives a slightly better soundness constant. So to emphasize that it's hard to find locally testable quantum codes, let me first say that the most famous quantum codes are not locally testable. For example, the toric codes, if you have a string-like chain of errors, it has syndrome only 2, so constant syndrome, which shows that it's not locally testable. And as I was saying before, for quantum expander codes, if you take errors of weight square root of the number of qubits, then they won't be, they can have a constant weight syndrome, so they won't be locally testable either. Now this brings me to the construction itself of this work. It's called the hemicubic code, and it has the following parameters: only one logical qubit and a distance that is that grows like square root of the number of physical qubits. It also comes with an efficient decoder, and in the work we have a generalization with more than one logical qubit, with a polynomial number of logical qubits. So the construction itself comes from the n-dimensional cube. It's not exactly the n-dimensional cube. You have to take quotients. So take a quotient of this cube. So identify opposite edges, opposite vertices, and opposite faces. And when doing so and using the usual homological construction, for instance, by identifying qubits with two faces with squares, you get a quantum code with one logical qubit. And it's possible to show that the product of the two minimum distances is the number of physical qubits. And to show local testability is the same as showing filling inequalities for such a code. That's because the syndrome of a homological code is like the boundary of the faces corresponding to the qubits that have an error. And to do this, we actually leveraged the work a work by Dotter from 2012 to show that in a cube you always have a small filling, and this filling can be of weight linear in the weight of the error. So the proof is recursive. You actually send you find the beginning of a filling that sends all the error to the left side of the n-dimensional hypercube, and then you can iterate with an n-1 dimensional hypercube. And this works well for the cube. The problem is that our quantum code is actually based on a hemicube, a cube with identifications. So we had to adjust the proof, and by doing so, we lose a log factor, which explains why the soundness constant is not optimal in our work. But we actually conjecture that the soundness constant of the cube is the right one, even for the hemicube. So to summarize and give some perspectives, we gave two constructions of quantum codes based on n-dimensional cubes. The first one, there is only one identification, and this gives only one logical qubit. And we can show that such codes are locally testable. And then a general version has a polynomial number of logical qubits, but is harder to analyze. And the main open question is to see for which growth of logical qubits we can find some quantum locally testable codes. Thank you.
The next talk is sharp threshold rates for random codes. with Nicolas Resch giving the talk.
Yes, great. Thank you very much for the introduction. This is based on joint work with Venkatesan, Jonathan Mosheiff, Shashwat, Silas, and Mary Wootters. So the topic for this talk, as I'm sure most of the talks in the session are error correcting codes, which are a means for two parties to communicate, even if they are connected by some sort of unreliable channel. So Alice here wishes to transmit a message to Bob, but for whatever reason, the channel might introduce some errors. So how would these parties deal with this? Well, they'll use what we call a code, which is just sort of a set of possible strings that Alice might transmit across the channel. And we'd like that this set of codes has some sort of error correcting capabilities. And this is in tension with the rate of the code, which is somehow a measure of how much information Alice is transmitting every time she sends a code word. And so in coding theory, we're basically interested in understanding what sort of trade-offs we could hope for between error tolerance and rate. In this talk, let's just, for concreteness, think of the alphabet sigma as being a finite field with q elements for a constant q, maybe even q equals 2 if you like, and we'll let the block length n tend to infinity. So specifically in this talk, we'll be interested in random codes, which you could just think of as sort of a uniformly random subset of the space sigma to the n, or if you prefer with, to be a bit more precise, we'll actually say that each element is included independently with probability chosen so that the expected rate of the resulting subset C is R, which is the rate of the random code. And so why would we consider these things? Well, this is a combinatorial, codes are combinatorial objects, and there's this interesting phenomenon that in combinatorics, random objects often are the best for a given problem. Also, from a more coding theoretic perspective, they're used in proofs of many classical coding theorems. As an example, one of the very first theorems that was ever proved in coding theory, Shannon's noisy channel coding theorem, uses random codes. They also appear in certain proofs of, say, the Gilbert-Barshimov bound. Another example, which is particularly relevant to this work, is the list decoding capacity theorem. So to describe this, what this theorem is, I'll first say what it means for a code to be list decodable. I have the definition written formally above, but informally, it basically means that whenever I take a ball of radius p, which is just the set of all strings that differ from the center x and at most pn coordinates, I never collect too many code words. So say there are always less than capital L code words in any ball of radius p. So what does the list decoding capacity theorem tell us? It essentially tells us how large the rate can be if we would like to have a code which is PL list decodable for reasonable values of L. Specifically, if the rate is at most 1 minus h sub q of p minus epsilon, where h sub q of p here is this Curie entropy function. If you're not familiar with it, you could just think of, say, the binary entropy function. We know that there exist codes that are list decodable up to radius p with lists of size only 1 over epsilon. But whenever the rate r exceeds 1 minus h sub q of p plus epsilon, say, then we can't really have list decoding in any meaningful sense unless we allow the list size to be exponential in n. What's interesting about this theorem from our perspective is that to prove the possibility result, we actually use a random code. So essentially one chooses a random code of rate 1 minus h sub q of p minus epsilon, and shows that with extremely high probability, it will be p 1 over epsilon list decodable. Okay, so this is sort of first example of what one might think of as a phase transition. Now I'm going to do a somewhat annoying thing. Somehow in this work, it was more convenient for us to talk about properties like the property of not being list decodable. So what did the list decoding capacity theorem tell us? Well, it said that when the rate r was very small, a random code is not list decodable with a very low probability. So, with probability very close to 0 will be not list decodable. Then at some sort of cutoff, it goes from being not list decodable, it goes from being not list decodable to not list decodable over a very narrow window. So we have this sort of a phase transition where the probability goes from being very close to 0 to very close to 1 over a narrow window. And so while the list decoding capacity theorem gives us some information, pardon me. There we go. While the list decoding capacity theorem gives us some information about these sorts of phase transitions, we could ask for more information. For example, like what sort of properties would experience such a phase transition for random codes, and also can we compute kind of this threshold rate where we go from the probability being very close to 0 to very close to 1. Say a motivating example where, say, the list decoding capacity theorem doesn't tell us anything. What if we care about something like p comma 10 list decoding, where the list size is fixed to this constant 10. Can we say anything about what sort of threshold rate we could get? And do we even have this sort of sharp threshold? So what do we do in this work? Well, essentially, we answer this question affirmatively. What we do specifically is we characterize this threshold rate for a large class of properties. And on this slide, I'll try to informally outline what we do. So first of all, we take the perspective of looking at many code properties, and we note that they're satisfied if and only if a minimal set of vectors happen to lie in the code. So for example, if we want to talk about the property of not being P-L list decodable, a code will not be P-L list decodable if and only if it contains some minimal set of L vectors from a radius P ball. Right, so we have kind of all sorts of these minimal sets, and we just need to ask, when is it the case that a random code is likely to contain one of them? And sort of building on some previous work and also using a concept from information theory called types, there's a natural way to go from these sets of code words which define the property into collections of what we call types. I won't be able to in this short time explain exactly how we do this, but all I need you to know for the remainder of the talk is that types are some sort of special distributions. Okay, so we can talk about the entropy of these types and things like that. And then essentially, based on what we've done so far, we could say that a property is satisfied if and only if some set of code words with one of these types happens to lie in the code. Right, so we can go from talking about some property to a set of types, and we just need to ask when a set of code words with one of these types happens to lie in a random code. And as a final step, which was actually sort of one of the more subtle issues in this work, we define what we call symmetric properties, which include things like list decoding and some of the generalizations like, say, list recovery. And we're able to compute the sharp threshold rate for any symmetric property. So one of the challenges here was to come up with a definition of property which was broad enough to include the things that we were interested in, but also narrow enough that we could give a very, very precise answer. So allow me to briefly show what the characterization of the threshold is. So basically, we can say that whenever you have a symmetric property, which is defined by the inclusion of a set of B vectors whose type lie in some set of types T, the threshold R star is always given by some sort of a quantity which depends on the entropy of the types in the set T. So recall I said that all these types, we can think of them as distributions. So talking about their entropy makes sense. Actually, we sort of use the Q-array entropy just because we're working over alphabets of size Q. Okay, so that's all I was planning to say in my 8 minutes. So all I did was sort of this first bullet point, the characterization of the threshold rate for symmetric properties. However, in the in the paper and also hinted at in the full version of this talk, we also talked about a few other uses of this characterization of the threshold rate. So we could give analytic estimates for the threshold rate for something like noisy list recovery, which is just kind of a generalization of list decoding. We also show that we can always compute the threshold rate as long as you admit some small additive error. We could even precisely pin down the threshold rate for something like, when we have the list of size 3, say, for binary random codes, we can precisely pin down the threshold rate. And also for a certain class of codes called perfect caching codes. Great, that's all I wanted to say. Thank you very much. Right.
Our next speaker is Farrokh Labib on high-entropy dual functions and locally decodable codes.
Yes. Let me go full screen here. Okay, can you see the slides? I guess yes. So my name is Farrokh Labib. This is joint work with Briet on high entropy dual functions and locally decodable codes. So I will first explain a certain interesting connection between locally decodable codes and Zémor's theorem with random differences, and show how certain objects called dual functions play a role here. So locally decodable codes encode some message of length m into a code word of length say n, and they have the property that you can retrieve a single message bit with high probability by only querying a small number of code word symbols, in this case 2. even after partial corruption. Some examples of locally decodable codes are the Hadamard code. This is a 2-query LDC of length exponential in M. And the Reed-Muller code generalizes to Q queries and has length exponential in M to the power 1 over Q minus 1. And for a long time, these has been the best codes, LDCs. And in breakthrough work, Yeganen constructs so-called matching vector codes, which are 3-query LDCs of length exponential in M to the power 1 over T, where he uses large families of matching vectors in FPM for Mersenne prime P equal to 2 to the T minus 1. So as of now, the largest Mersenne prime has T at least 77 million. So as you can see, this is a huge improvement over the 3-query Reed-Muller codes. And later, Flamenco constructs 3-query LDCs of sub-exponential length using matching vectors in Z mod L to the power n with L composite. And as was noted in the previous talk, most of the time the probabilistic method can beat certain constructions easily. For example, expanded graphs. But in the case of LDCs, this is not the case. The probabilistic method has not beaten such explicit constructions here. So a certain framework where this can be done is the framework by Briet, Leverrier, and Gopi, where a special instance is given by Zémor's theorem with random differences, and it uses the probabilistic method to construct LDCs. And I will now explain what this Zémor's theorem with random differences is. But first, Zémor's theorem. So suppose you have a wheel with a lot of spokes, and say you remove 99% of them. So these are the remaining ones. And then if the number of spokes that you started with was very large, then the remaining ones will always contain some structured subset, the red spokes here. And the structure is that subsequent spokes have equal distance. Precisely, any subset from from 1 up to n, with A having a positive fraction of all the elements, contains a non-trivial k-term arithmetic progression, which is a sequence of the form x plus d, x plus 2d, ... x plus k minus 1d. And this is true when n is sufficiently large. So a certain refinement of this is called Zémor's theorem with random differences. And here the question is, what is the smallest row k for which a Bernoulli row k random set D inside an abelian group G? We can do this for any abelian group, such that it has a property that Zémor's theorem holds with common difference inside D with probability at least 1/2. So what I mean is, I want this statement to be true, but I restrict my common difference, the step size here, to be inside a Bernoulli row k random subset from, say, the interval from 1 up to n, or any abelian group. And it is this row k that we try to find. And this probabilistic framework of Briet, Leverrier, and Gopi uses this as follows. They show that there exists k-query LDCs with message length omega row k of that group G times n, and codeword length O of n, where n is the size of the group. So if row k is large for a certain group, that gives you good LDCs. So in this framework, it's important to understand the upper bounds on row k, so we can understand what kind of codes we can find from this connection. And a conjecture by Frantzikakis, Lesage, and Weird state that this probability row k for the group Z mod n is at most log n divided by n. And if you work out the details, the truth of this conjecture would imply that in this framework, Zémor's theorem with random differences cannot give better LDCs Danne-Hadamard code over Zémor n. And similarly, it is expected, but not explicitly stated as a conjecture, that over Fpn, this probability rho k is at most n to the power k minus 1 divided by p to the n. Again, if this is true, Zémor's theorem with random differences cannot give better LDCs than the Reed-Muller codes of this group. So in this work, we mainly focus on the finite field case, and this explicit conjecture is mainly motivated by a conjecture in higher order Fourier analysis, which is this conjecture is a finite field analog of a conjecture made by Francis in ergodic theory, and the precise conjecture is, or this is rather imprecise, and it says that objects called dual functions can be approximated arbitrarily closely in L infinity distance by low degree polynomial phase functions. I will explain what are these objects later, but for now, conjecture 2 implies conjecture 1. So if conjecture 2 was true, then this upper bound holds, and we cannot get better codes than Reed-Muller codes using this probabilistic construction. But our main result is that conjecture 2 is false. So let me define what these objects are. So an order 3 dual function is a function from Fpn to the complex numbers. It's given by some pattern ijk, and it takes the following form for some functions fgh, and it's an expectation. So what are polynomial phase functions? These are simply of the form a p root of unity to the power a polynomial p of n variables of degree at most k. So the conjecture states that any order 3 dual function can be written as some convex combination of these functions of degree of polynomial phases of degree at most 2, and the error term in this decomposition is small everywhere. It has small L infinity norm. And we show that that is false. And in fact, we can define order k dual functions for any k, and that's our result says that we cannot approximate such functions using only polynomial phases of low degree. And a proof sketch goes as follows. We show that there for infinite many primes there is some set of order k dual functions such that it contains a high dimensional hypercube. Then we use the fact that there are not so many polynomial phases, and then we conclude by using some tools from geometric function analysis. It's a very rough sketch. And let me conclude by some open problems. So the counterexamples we found, we don't have really good control over the patterns, and would like to have examples for 3 epidual functions, and maybe even for more primes, like for large enough primes, there should always be counterexamples. And the upper bounds on Zémor's theorem, but random difference is still open. So thanks for your attention.
Thanks. The next paper is error correcting codes for uncompressed messages, and Ofer Grossman will be giving the talk.
Hey. Cool. If you can't see this, someone speak up. But yeah, I'll be talking about error correcting codes for uncompressed messages, and this is joint with Justin Holmgren. Cool. And so here's the setup that we're all familiar with. There's like Alice, she has some message, in our case, this picture of an apple that she wants to send to Bob. And there's a channel where there's some adversary that can corrupt, in our case, up to 3% of the bits. 3% is arbitrary, but yep. And here we'll assume that Alice is a polynomial time machine, and Bob is a polynomial time machine. All right, so she wants to somehow send it to Bob so that even if there's errors, Bob can still recover the original message. All right, great. Cool. And so the standard approach when we do these things is kind of first we compress the message and then we use an error correcting code. So it's kind of a two-step process. So the reason it's important at first to compress the messages is well, if you have this picture of an apple and you have some image compression algorithm that can, in a lossless way, compress it to say half its size, then at the end of the day, you're going to be saving half your bits. You're going to be sending half as many bits. So kind of there's two ways in general to save. You can either get better compression algorithms for whatever type of message you're sending, or you can get better error correcting codes. So it's this two-step process. Right, and in this case, an error correcting code is something like this. It's a pair of algorithms, an encoding and a decoding algorithm, so that whenever I encode something, add errors, and decode it, I get the original thing. It's just a standard error correcting code definition. And this is where the new stuff starts, as we kind of ask, is this the best we can do? Is it really true that the best we can do is to compress the message and then use an error correcting code? And it turns out that that's not always the case. And so let's think, for example, about a situation where our message, we don't know how to compress it to the information theoretic limit, right? For example, it might be the case that because of computational limitations, we can't compress it to the limit, or maybe we just don't know what the algorithm is, or maybe there is some structure and we don't know what the structure is, so we can't use it. But there's a bunch of reasons why our compression algorithm might not reach the information theoretic limit. And then what happens is when we go to the step 2, our message still has some sort of structure. So using this very general error correcting code is kind of overkill, right? There's still some sort of structure. So even if we can't kind of harvest the structure to get better compression algorithms, it might still be the case that we're able to use the structure to get better error correcting codes for that specific message or for that specific class of messages. So the idea is, in a sense, to combine 1 and 2, or just to kind of throw away this compress and use an error correcting code and think what is it that we want in general, and how can we leave the standard approach and see if we can get something better. So here's the new approach. The new approach will be, we'll try to create an error correcting code that guarantees that it will definitely work for all reasonable messages. So the way we can think of these reasonable messages is, for example, in the case of images, it's everything that actually looks like an image. So for example, a picture of an apple is reasonable, and something that's a random matrix of pixels is not reasonable, right? And you can think a random array of pixels is not compressible, whereas a picture of an apple is compressible. So yep. So the idea is we want to somehow be able to get error correcting codes that work for these reasonable messages. All right, so here's a definition. An error correcting code for a set S, where S we can think of as the set of all reasonable images, is an encoding and decoding algorithm so that for all X and S, when I encode it at errors and decode, I get X again. Right, so the difference from our previous definition is that here my guarantee is only over X and S. Earlier I had a guarantee over all 0, 1 to the K, and now I have a guarantee over X and S. And this is actually what we care about, right? If you're Alice and you're sending a message to Bob and you're sending this image of an apple, you only care about how the error correcting code behaves on actual reasonable images, right? We think of S as a set of reasonable images. So you only care about how it behaves on these reasonable images, because you're never going to be sending Bob a random array of pixels. You're only going to send him things that actually look like images. So having an error correcting code that's guaranteed to work on these things that look like images is exactly what you want. So this leads to the question of okay, for what sets like this can you build this thing? But before we talk about what sets we can build this thing, let's just see an example so the definition is super clear. So suppose Alice has this picture of an apple and she wants to send it to Bob. So this picture of an apple is in S because it's a reasonable image, right? So we can imagine it's in S, so then Bob gets it and the error correcting code succeeds. If Alice has random noise, this doesn't look like an image, so it's not an S. So Bob gets this other thing that's different, and the error correcting code fails, but we don't actually care because Alice is not going to send something like this in the first place, right? So here I'm always thinking of S as the set of these like reasonable images, but you know, if you're sending different types of data, you can think of S accordingly, right? Like if you're sending English text, you can think of S as everything that is not just like random keyboard mashing, but everything that actually looks like English text. All right, cool. So with this in mind, now the main question is for what S's can we construct these things? So here's our result. And here I just like picked parameters so there wouldn't be a bunch of like weird expressions. So we show, for example, that for every set S that's small enough, where you can determine membership in S in polynomial time. So given an X, you can tell whether it's an S or not in polynomial time. Then there exists an error correcting code for S for 3% errors that expands the message by a factor of 1.74. Right? And to compare with this, with what was known before, is what was known before if you did the old approach was 2.52. If you use this old approach of like just using a normal error correcting code, not these error correcting codes for a specific set, then after our work you can get 2.27. But the main point is that they're both far from 1.74. So using this old approach gives you something much worse than the new approach. Like And yeah, it's worth noting in general, like here I just picked parameters because it's kind of complicated to write the exact expression. So I figured picking parameters would be a better example. But in general, there's just a continuous trade-off between the size of S, the amount of errors, and the rate. Cool. And then like 30-second like the approach uses list decoding. So list decoding, I have a message, and then when I decode it, I get a list. And the idea is like kind of if you're Bob and you get this list that looks like this, you can see that a lot of the things kind of look like nothing, and then one of the things looks like an apple. So if you're Bob and you receive these, you can kind of guess that the apple is the message that Alice sent. So formally, the idea is we kind of want to create these list decodable codes and augment them so that we can guarantee that with very high probability, only one of the elements in the list will be an S. So then we can check each one of these elements in the list if it's an S or not, and then we just take the one that is an S. Yep, so that's it. Thanks.
Thanks. And the last speaker is Yuval Dagan on the entropy of lies, playing 20 questions with a liar.
Hello. Yeah, so this is a joint work with Yuval Filmus, Daniel Kane, and Shai Moran. And this work is about the 20 questions game. So let's start by describing the simplest variant of this game. So it is played by two parties, Alice and Bob, where Bob thinks of some object from a finite set, and Alice's goal is to reveal this object using yes-no questions. So here you can see a strategy of Alice, and Alice wants to ask as few questions as possible. So in this simple variant of this game, the optimal strategy will ask log n questions, and this is achieved using a simple binary search. So now let me add, I will add two different complications of this game. So the first complication is by allowing Bob to answer some of the questions with lies. And he is allowed at most k lies. And Alice would have to figure out the true element always, regardless of the lies. And this was studied in prior work already in the 60s and 80s. And the optimal strategy requires an additional k times log n questions. So that was the first generalization. And let me explain the second generalization. And here we assume some probability distribution over the element that Bob selects. This probability, we call it mu. And Alice knows this distribution. And her goal is to minimize the number of questions that she asks in expectation, where the expectation is over this probability distribution. So let's see some examples. So here we have the potato will be selected with probability 1/2, the cat with 0.3, the dog with 0.2, and what is the expected number of questions that Alice asks in this strategy. So it can be easily computed to equal 1.5 questions on expectation over a random object. So once we define this, setting, now we can ask what is the optimal strategy for Alice. And first, in the setting with no lies. And the optimal strategy is easily obtained using a Huffman code. And it asks roughly the entropy of the distribution number of questions on average, where the entropy is just the sum over all probabilities mu I of mu I times log 1 over mu I. So I defined two extensions of this game, first by introducing lies, and then by introducing a probability distribution over the elements. And both were studied separately in prior work. And in this work, we study a mixture of these settings, namely both a distribution and allowing Bob to lie. And in order to show the guarantees of obtained in this paper, so let's recap the prior settings. So in the deterministic setting with no lies, we have log n questions. With lies, we have an additional k times log n questions. Now in the distributional setting, the log n is replaced by the entropy of the distribution. And in this paper, we show that in the distributional setting with lies, we can further replace the log n by a term that we call the H2 of the distribution, which is just the sum over the probabilities of the probability times log 1 over the probability. And we noted that if we substitute the uniform distribution into mu, then we get the same number of questions as in the deterministic setting. So this is some kind of an extension, and we have both upper and lower bound that are with sharp constants up to some lower order terms. And further, the algorithm is efficiently computable and uses a binary search-like algorithm. So it uses only comparison queries. And for this reason, we can apply it to sorting with comparison queries. So in the sorting setting, so we have a noisy sorting where some of the comparisons can give you wrong answers. And we assume a distributional setting, which means some prior distribution over the possible permutations. For example, we can assume that the array is already partially ordered. And in this setting, we can replace the n log n comparisons with the entropy of the distribution over permutations. So yeah, actually I have some time, so maybe I can just, okay, so yeah, it was closed, so I wanted to show the lower bound, but you can see it in the video. And yeah, thanks for watching.
let's open the discussion. You can ask questions to the speakers, or you can discuss any general topics regarding codes.
Sure, wait, can I ask a quick question then? To the last speaker, Yuval, I was wondering, so this H2 of mu quantity, it sounds, did you define this quantity, or has it been, are you aware of it being used in any previous works, or is it just really, is it something that popped up for the first time in what you were doing?
I know. I mean, it is just, that's what you get. So you have some like conditional entropy, and it comes from the expected log 1 over the number of questions. So that's how you get it. I don't know if it was defined before.
I see. So it's not like you're applying some other fact where it appears or anything like that. It's really just comes out of the analysis itself.
Yeah, it just comes from the analysis.
So I have a question to the first speaker, Vivien Londe. So I'm wondering, is there any way how one could transform a classical LDPC into a quantum LDPC?
There is a construction called the hypergraph product construction by Silas and Zémor from 2014, and it takes it takes a classical LDPC code and makes a quantum LDPC code. It's like a product, but you lose some properties of the classical code by doing so. So in terms of the minimum distance, under some mild assumption, you will only get square root of the minimum distance of the classical code. And in terms of local testability, you can lose also some soundness property by doing this product.
Okay, thanks.
I had a question for Ofer. So this set, so in your work, you assume that the set is like efficiently testable, right? By a polynomial time algorithm. Do you have any positive or negative results about what happens if that set is not testable?
I think you can show that there exist sets where you can't do anything. Like if you pick a random set, then I think you can show you can't really do much. Mm-hmm. But there might still be things that are like structured, and also you can't like tell membership quickly, but you can still encode them. This I don't know.
Okay.
So there is a question in Q&A by Mayank Bhaskar. The question is to Ofer Grossman. What is the complexity of new contextually error correcting code with negligible error with respect to the baseline approaches?
Wait, can you say that again, or is it written somewhere?
It's under Q&A.
I see it. What is the complexity with respect to the baseline approaches? So it's all polynomial time. I don't know exactly how the polynomial time compares with the standard approaches, but basically everything we do is we just take like known list decodable codes and then we augment them a little. So whatever complexity your list decodable codes have, this is going to have the same complexity as them. Yeah.
If I can ask another question then, can you say anything about the list decodable codes which you use?
You can use basically and you need them to be like to be both like efficiently list decodable, and they need to have like some combinatorial list decodable properties. So,
so I mean something like folded Reed-Solomon code, or even just a Reed-Solomon code list decodable after the Johnson bound, that would already give you something, or
yeah, you get something from any list decodable. You get code, you get something, you get like an improvement. But if you want to be like get the best bounds, you have to be kind of careful about.
Okay.
Yeah. But even just using like the most standard things will give you improvements, though not like the best bound that we achieve. Yeah.
Okay. Also, I guess I could ask another question to the second speaker. If I understood correctly, there were sort of two conjectures, and there was a conjecture which you refuted, which would have implied the other conjecture, which was sort of about the the bound on row K. Do you have any intuition as to whether or not that bound is the correct bound, whatever is like n to the k minus 1 over p to the something, I believe? Do you think that that expectation or conjecture is still likely to be true?
Yeah, so there's this lower bound proven by my co-author, Briet. And it's basically this upper bound that I showed is, he showed that this specific lower bound holds. So if this upper bound would be true, then his lower bound would be optimal, and then things would be fine, or not so good for this probabilistic construction of the LDC. But yeah, it's still open whether this is true or not. It's like an analog of this of Z mod n, where these people also proved the same lower bound, and then later conjectured that this should be also the right upper bound. But it remains open. It's a hard question, yeah. So if this conjecture on these dual functions would be true, then these upper bounds would be the same as the lower bounds. And so the counterexamples of dual functions that we gave actually do not correspond to certain dual functions that are called 3AP dual functions, or KAP, K-term arithmetic progression dual functions. So where the pattern is some specific pattern corresponding to arithmetic progressions. And so the counterexamples that we have found, we don't have good control over the pattern. So we haven't yet constructed counterexamples to the arithmetic progressions. So that would be interesting to look further into.
Oh, I see. So you'd want the pattern to be like 0, 1, 2 up to k minus 1, I guess? Is that
exactly
the ideal thing? But you can get arbitrary I1, I2, IK.
Exactly. So it's we don't have control over that. So we try to find certain polynomials that satisfy certain properties, and so the pattern that we then get after having found this polynomial that has its good properties, then the pattern is simply the powers of the monomials. So
I see. Like the sum of the degrees of the monomials? Is that what you mean, or?
No, so if you have some polynomial, say 1 plus x to the power 3, then the pattern would be 0, 1, 3.
I see.
Powers of
the
monomials,
Yeah.
And so we actually showed that in the framework that we are using these matching vectors, and we cannot find polynomials satisfying the right properties where the powers of the monomials are a K-term progression. So the way we are doing it right now, we cannot find counterexamples, but there might be another way to do it.
Cool. Also, this might be too technical to say briefly, but can you say anything about how, how you get these constructions of LDCs from these sort of results on this Simradi's theorem with random differences?
Yeah, so in this framework by Briet, Vivien, and Gopi, they give a characterization of LDCs in terms of certain probability distributions over smooth Boolean functions. So it's like a one-to-one correspondence between these two between these two sets, and somehow these the Simradi's theorem with random differences can be seen as a special instance of these probability distributions over smooth Boolean functions. So I don't know exactly how this is exactly done, so how this probability distribution is constructed using this Simradi's theorem with random differences, but that's basically how it's done. So there's this characterization of LDCs in terms of certain probability distributions over Boolean functions. Yeah.
And this might again be kind of technical, but wait, are the LDCs then smooth? Like, is it like you can randomly sample any, like if you're doing like a three query LDC, is it like you can sample any 3 coordinates, or do they have some sort of, is like the query distribution somewhat?
No, so smoothness is about the Boolean functions. So you want the Boolean functions to be smooth, and it's some kind of property of the some spectral norm of the function has to be, I think, small, something like that. That makes it smooth, but it's not something to do with the with the LDCs. It's just functions are smooth. Yeah.
So if there is no further questions or comments, let's thank everyone. And the next session is starting in 2 minutes in the other room.